Okay, folks, let's get started. Again, thank you for joining us today for the California Fire Science Seminar Series. My name is Nick Dutch, and I'll be your host today. I'm a member of the student committee who assisted with organizing the California Fire Science Seminar Series. I work with UC Cooperative Extension with the Post-Fire Forest Resilience team up in Quincy, California, and I am a UCLA grad student studying GIS at the moment, and previously was at UC Berkeley studying forestry. And I'm really excited for this talk that we have today. The California Fire Science Seminar is organized and supported by the California Fire Science Consortium, the Fire Research Group, the University of California, Berkeley, and the University of California, Merced. The student committee was also integral to the success of this seminar series, which also included 18 students and postdocs from across the nation who helped select speakers and topics for the series. This webinar is being recorded and will be posted on the California Fire Science Consortium website and YouTube channel. Following today's presentation, there will be a Q&A session. Please feel free to add any questions you have to the Q&A chat throughout the presentation. Today's seminar, Shifts in Seasonality and Increases in Hydroclimate Whiplash Are Increasing California Wildfire Risk, will be presented today by Daniel Swan. Daniel Swan is a climate scientist focused on dynamics and impacts of extreme events, including droughts, floods, storms, and wildfires on the warming planet. Daniel holds joint appointments as a climate scientist with California Institute of Water Resources within UCANR, the Institute of Environmental and Sustainability at UCLA, and as a research fellow for the NSF National Center for Atmospheric Research. I don't know if you guys have seen his Weather West YouTube videos, but they are quite awesome, and he engages extensively with journalists and other media partners, serving as a climate and weather science liaison to print, television, radio, and web outlets to facilitate accessible and accurate coverage and conversations surrounding climate change. And now please join me in welcoming Daniel Swan, and feel free to start your presentation anytime.
All right, well, thank you for that introduction and for the invitation to speak today with this group. I know there's a lot of interest, of course, given not just recent events, but events over the past 5 or 10 years in California, particularly on the seasonality aspect of this. And so I'm just going to go ahead and dive right in. So just to motivate this, this is an evolving slide I've presented for other audiences who are perhaps a little bit less fire aware. But I do think it's worth reiterating a few things, and I did update this past week because there are some new statistics to share. Of course, acres burned, as many of us know, is not always the most useful metric in describing wildfire trends in terms of the human impacts or the ecology of fire, but it is, for better or for worse, one of the better measured metrics going back for a longer period in time. And we have seen, as of early 2025, 13 of California's 20 largest modern era wildfires just since 2015. So now within the past decade alone, but perhaps more importantly, 15 of 20 now, so 75% of California's most destructive fires have now occurred in the past decade. 5 of them occurred in 2020 alone, and 2 of them, the pair of fires in Southern California just last month, occurred this year. 9 of the 20 deadliest fires, again, since 2015, 2 each in 2020, and unfortunately, again, the Eaton and Palisades fires are on that list just this year. But this is a statistic that I've really was a little bit surprised when I dug it up. But it remains even more true than it did a couple of years ago when I first started crunching the numbers, that more people have been directly killed by wildfires. It's now over, the death toll is now over 260 since 2015, than in all California earthquakes since the Long Beach quake in 1940, and in any single earthquake in California since the Great Quake of 1906 that devastated San Francisco. So, of course, wildfires and earthquakes are not the same type of natural hazard, but I just want to reflect for a moment that for many years, California's natural hazard anxiety centered largely around solid earth geophysics earthquakes. And it turns out that in this current moment, and this may not always remain the case, but at least over the past decades, wildfires have been far deadlier at least in a direct context, than really most other kinds of disasters. And I think that is not necessarily something that had been anticipated prior to the previous 10 years. The only other piece I wanted to illustrate with this on the right is that we often hear about the mean trend in the last several decades towards increasing acreage burned in California and elsewhere. But the thing I find a little bit more interesting on this is the increasing variability of acreage burned over the past several decades in California. There is, of course, a trend on an average, the average numbers, but what you can really see is there's a huge variability year to year. There are some really enormous fire activity years, but also a lot of years that are just as quiet as most of the historical quiet years. So what's really happening is the most extreme years, these years with episodically very large extent of acreage burned and of fire-related losses, that is what is increasing. So it's not so much that there is even a typical fire year at this point. It's really this increasing range between pretty quiet years that are similarly quiet to the ones we used to experience, but now very extreme years that are quite a bit more extreme than the ones that we were used to for most of the 20th century. So at scale, what's driving what I think is pretty clearly a crisis, the escalating wildfire crisis? Well, there's obviously more than one factor at play, and of course, anybody who tells you otherwise is not telling the full truth about the situation. There is, of course, the influence, at least from a structure loss and lives loss perspective, that there are simply more people and more stuff in potential harm's way. The expansion of populated areas well into high-risk zones, even the preferential expansion of neighborhoods and suburbs into places that we know and have long been at high risk of fire. The reality that the inhibition of natural fires for a good portion of the 20th century across much of the West, this is especially true in many forested ecosystems, is a contributor to an ecological fire deficit, which has increased fuel loading. And there are also other land management decisions in non-forest ecosystems that are really important as well. And this is, of course, more relevant in places where we see destructive fires that are not forest fires, much like the ones we saw in Southern California in January. Then there is, of course, climate change as well. And, it certainly isn't the only factor, but many times it's a very important one. And it's also the one that I'm going to primarily focus on in today's talk as a climate scientist and a meteorologist, but just always like to acknowledge the fact that it's not the only factor at play, even if it is the factor that I tend to emphasize the most as a climate scientist. So just as a quick overview of where we are with global warming, and I just pulled this most recent long-term warming trend plot just a couple days ago from NASA. It gets more orange and red every year, as you might expect in a warming world. There are changes, of course, in Earth's climate beyond temperature. So we talk about global mean temperature increasing, which is, of course, occurring, and we know why it's occurring due to the increase in accumulation of heat-trapping greenhouse gases in the atmosphere caused by various human activities. But there are, of course, changes in Earth's climate beyond temperature, and often those are the ones that may actually end up being quite relevant from a fire risk perspective. We've warmed, depending on how you measure it, in a long-term decadal context by about 1.3, 1.4 degrees centigrade. But the last couple of years, so 2024, 2025, or sorry, I guess we're not through 2025, but 2023 and 2024 at least, we're both at or above 1.5 degrees centigrade of global mean warming in most temperature data sets. So we have seen a stair step upward over the last few years, and the Earth has been exceptionally warm in the past few years, even relative to recent decades. So there has been a bit of a spike on that warming trend in the last few years, even though overall the amount of planetary warming is roughly in line with expectations even from some decades ago. And we're currently on a path globally to approximately double the amount of global warming we've seen so far. So by later in the 21st century, probably still on a track for around 2.5 to 3 degrees centigrade or 4.5 to about 5.4 degrees Fahrenheit of global mean warming. But of course, those numbers don't really tell us most of what we need to know about the connections between climate and wildfire in any given place on Earth. So zooming in to California here, we know, of course, that California is a warmer place than it used to be. The summer heat has increased faster than temperatures at other times of year. Uh, California's three hottest summers on record have now all occurred in the past decade, and they've been successively hotter. So we experienced this first in 2017 with a record-breaking year, and then a few years later again. And just this past summer, in fact, on a statewide basis, was once again the hottest summer on record. It wasn't everywhere in the state. In fact, some of the coastal areas were on the cooler side this past year, but that was so hot across inland and mountain areas that it completely offset that for the statewide statistic, making summer 2024 the hottest on record for the third time in the past 7 years. As I mentioned, that warming has been faster across inland areas, so hotter areas, pre-existing hotter areas are getting warmer faster than the traditionally cooler regions along the coast, and also at higher elevations. And this has ended up being really important from a wildfire perspective because the thermal belt in the hills and mountains, ringing the Central Valley in particular, have warmed in recent years at a pretty incredible rate. But as I mentioned, temperature isn't the only story, and just to give a big picture again, thinking about how precipitation and importantly the character of precipitation is changing in a warming world, well, global mean precipitation increases relatively slowly, but it does increase with warming by about 2 or 3% per degree centigrade. But if you take a look at this map on the left here, and I'm deliberately using an older figure here, because quite frankly, even with newer climate modeling generations, these figures haven't changed much. Uh, Although there is a global mean increase in precipitation, there are, as you can see, regions on Earth where precipitation either strongly increases or pretty strongly decreases. So what happens on average with precipitation in a warming climate really depends on where you are. It's not a homogeneous global picture. There's also lots of regions where there isn't a very strong change at all in average precipitation, or where the change is even uncertain in sign per degree of warming. Those would be areas that are either light green or light brown and don't have that black statistical significance stippling. Well, but then I want to really just compare, rather than zooming into the details here, the left map to the right map. And the right map is depicting changes in projected precipitation extremes per degree of warming. And there's really two things I want to highlight here. One is that there's a lot more statistical significance stippling. So there's much higher confidence that the wettest wets get wetter with each degree centigrade of global mean warming. And importantly, you can see that this extends even to places where there was no projected change in average precipitation, or even in some cases projected decreases in average precipitation. So our confidence in changes in the wettest wets is actually much stronger in most places in the world than in mean precipitation, which might sound counterintuitive, but I'll explain in a moment why that is. Also note that the magnitude is generally much higher. Global mean precipitation, again, only increases by 1 to 3% per degree centigrade, but the most extreme wet events likely increase by at least 5 to 10% per degree of warming, if not locally more. So it's a pretty big difference whether we're talking about the mean versus the extremes when it comes to precipitation in a warming world. And just to zoom into California again, I just really just I'm just popping out the boxes representing where California is on these maps. As you can see, again, California is a place where there's not really a strong indication of large changes in mean precipitation, nor strong confidence in whether it might be a bit of an increase or a bit of a decrease, but where there is, despite that, strong confidence that the most extreme wet events will become even more so. So what's going on here? And also what's going on with evaporation, the other side of the hydroclimate coin. So we also know that the relative humidity over global land area is expected to decrease a little bit, although global averaged relative humidity probably won't change very much in a warming climate, maybe a slight increase over the oceans and a slight decrease over land. There has been a somewhat faster than expected decline over some global land areas, including the American Southwest and much of California in recent years. Whether that persists or not is not fully understood at this point. But what I really want to emphasize here is that the thirstiness of the atmosphere, as quantified using the vapor pressure deficit, the gap between how much water vapor is in the atmosphere at any given temperature and how much could be in the air at that temperature, a related term being the atmospheric evaporative demand, these quantities rise as a function of fundamental thermodynamics exponentially with rising temperatures, even if there's no change at all in relative humidity. So let's make the reasonable first order assumption that relative humidity doesn't decrease at scale in a warming climate. That may or may not be true locally, but just make that conservative assumption. Even if we do, the thirstiness of the atmosphere, as measured by vapor pressure deficit or evaporative demand, is going to increase rapidly as a function of warming in most global land areas on Earth. So, what is that fundamental thermodynamics that I mentioned? Well, we can sort of visualize it using what my colleagues and I now like to call the expanding atmospheric sponge effect. And really, what this is representing is the tangible, real world consequence of what's known as the Clapeyron relation. My French is not great, apologies. But the basic idea here is that it's been long understood since the 1800s that the water vapor holding capacity of air itself rises exponentially with increasing temperature. This increasingly causes the atmosphere to act like a progressively larger kitchen sponge, capable of absorbing more water well, in the analogy from, say, you spilled some water on your kitchen counter, but also yielding more water if that expanded sponge is saturated. So that larger and larger sponge is the main reason why we see more extreme precipitation events, wetter wets, because if that larger sponge is saturated, it can yield more water. But on the dry side, this analogy works too, because of course, if there's no water to soak up, that larger sponge still has greater absorptive capacity than the small one does. And that is analogous to a warmer atmosphere in the absence of an increase in that relative humidity. It has an increasing propensity to demand water from the landscape in a warming world. And so on balance, the tangible effect of this is that the atmosphere becomes both thirstier when it's not saturated or when it's not raining, but also capable of much heavier downpours when conditions are conducive for precipitation and when the air is saturated. So all of this leads to a quantity that my colleagues and I have termed hydroclimate whiplash, which we define quantitatively in a recent review paper, but really qualitatively is just referring to unusually rapid or intense swings between wet and dry conditions. And again, these are relative to place and time. So we're not comparing the Sahara Desert to the Amazon or something. It's always an apples to apples type comparison, comparing a place to itself, even relative to its own seasonality. In this recent review, we surveyed around 200 existing papers and did a bit of summary analysis on our own on top of that and found that there's quite strong evidence in a warming climate that this hydroclimate whiplash or any number of measures of hydroclimate variability will increase with warming, and that these increases over decades will likely become strongest over land, largely because the warming itself is strongest over land, and there are some self-reinforcing feedbacks that develop there. We also find that this process is likely to accelerate somewhat between about 1 and 3 degrees centigrade of global mean warming. And of course, as I mentioned, we're now seeing years that are around 1.5 or even greater above the long-term pre-industrial average. And so we are right in that midst of the period where we might expect to see acceleration in this projected increase in hydroclimate whiplash. So that's the global view, but now I want to talk more specifically about where this fits into the California picture. As most folks who have lived in the state or studied fires in the state or fought fires in the state or managed fires in the state are very well aware, California has a bit of an unusual climate in a North American context and even to a certain extent in a global context. Mechanistically, that's because the region exists essentially at a climatological transition zone between the more stable subtropical climate regime to the south and the more active mid-latitude climate regime to the north. And this is not a fixed boundary. It shifts seasonally, as you can see in this animation of seasonal monthly average precipitation. Of course, it's dry in the summer in most of California and wet in the winter. That's the canonical cycle anyway. Sometimes it gets interrupted, but that's the general picture. There's also a strong latitudinal gradient. It's generally wetter in Northern California than it is in Southern California. And this repeating seasonal pattern can vary somewhat from year to year. So that boundary between the subtropics and mid-latitudes is farther south in winter. That's why we have a winter rainy season in California, and farther north in summer. That's why it tends to be dry. But it can also vary from year to year. Years that are particularly wet are usually years where that boundary is anomalously far to the south, and really dry winters are typically those where this climatological transition zone is to the north of California, somewhere up in the Pacific Northwest or Alaska instead. So all of this predisposes California not only to a typically high variation from season to season, but also high interannual variation in precipitation and high susceptibility to drought because there's generally only a few months in any given year when this part of the world is going to get its meaningful precipitation. So if we miss out on that December through March period any given year, we're kind of out of luck until the next cycle the following year. So you really only need to have an anomalous dry period for a few months during peak rainy season to develop a pretty significant drought. And that's not necessarily true in places that have a broader, smoother annual distribution of precipitation throughout the year. So what's been going on recently? Well, not a huge trend in the long-term average precipitation. There's a bit of a decrease in the past few decades, but it's not statistically meaningful at this point. We do see, though, an increase in late season moisture variability on a statewide basis. This is a bit of a clunky plot. I just pulled it up for a recent blog post, but you can do this for different regions within California and at different times of year, and you get a similar answer, which is that the variability in the landscape level moisture conditions has increased over the same period where there's not really been a big decrease in precipitation. But there's also been a strong increase toward holistically defined drought. And holistically here, I mean essentially drought metrics that take into account both precipitation and evaporation, or at least evaporative demand. And that's a metric that is frankly more relevant if you care about ecosystems, if you care about hydrology, if you care about wildfire risk, because of course, plants on the landscape are not only experiencing water falling from the sky, but what they're really responding to is the amount of water that's left in the soil, the net water balance that is the sum of both the precipitation and that water evaporating or transpiring back into the atmosphere. So we do see a trend towards more intense and frequent drought conditions in California, increased variability of moisture, especially in the second half of the calendar year, which is relevant to fire season, but not a tremendous change in the average precipitation. So why do these non-mean state conditions matter? And I have a few examples of why they matter. This was one of the first contemporary examples that I pulled up. I've been using this slide now for a few years. This harkens back to late 2017 and early 2018, which at the time, the Thomas Fire, which burned in Ventura and Santa Barbara counties, was the largest modern California wildfire, and it didn't start burning until December, and was not fully extinguished until early January in the following calendar year when a relatively localized but extreme downpour of rain caused a devastating and quite deadly debris flow in Montecito and parts of Santa Barbara. But if you take the average climate conditions over this 2-month period, you would characterize it as primarily sunny, somewhat breezier than average, and with below average precipitation over the 2-month period. Obviously, that characterization would completely miss the pair of quite different but related devastating disasters that occurred in this region over the same 2-month period. And it just goes to show that if we only consider these average changes in climate, then we're often going to miss the point when it comes to natural hazards in general, but and also specifically when it comes to wildfire. So we also have this more recent example where we have this pretty devastating example from Southern California just this past winter, from an extreme, what we would call wet to dry hydroclimate whiplash event with near record wetness last winter or over the 18-month period ending in June in parts of Southern California, a very hot and evaporatively demanding summer and fall, at least across mountain and interior areas, and then a very warm and anomalously atmospherically dry autumn virtually everywhere in coastal Southern California, followed by a complete failure of the rainy season to arrive in coastal Southern California, at least through late January. It did finally arrive, but not until it was too late from this fire's perspective. This resulted in a fairly dramatic vegetation accumulation in terms of herbaceous fuel in coastal Southern California, especially the grass and the lighter brush component, which grew quite prodigiously the past couple of wet years, with an exceptional vegetation desiccation and profound drying period all the way leading up to what ended up becoming devastating wildfires in the LA Basin in early January of this year, when traditionally strong, a bit stronger than usual, but the seasonality of these winds was not unusual. These strong offshore winds came along at exactly the wrong moment would be in this vegetation accumulation and desiccation cycle leading to the disasters we saw unfold. And just a bit of further context regarding these events, we do see specifically in the coastal Southern California chaparral ecosystems, which were primarily what were burning in January, about a 25% increase in late season moisture variability. This is relevant, especially because this is offshore wind season. So when we talk about the magnitude of individual extreme fire weather conditions, so essentially the most intense fire weather index values during peak offshore wind season, which in coastal Southern California is generally November through January, we see since the early 1980s about a 36% increase in the maximum amplitude of those extreme fire weather days during peak offshore wind season. And that's important because it means that the co-occurrence of these extreme ambient dryness conditions and these strong offshore wind conditions has increased quite a bit, not necessarily because the winds themselves have changed in a meaningful way, but because the vegetation critical dryness frequency has increased to the point that the joint co-occurrence is greatly elevated, and we're seeing that manifest. So all this is interesting in light of what we expect to see are projections for precipitation in California in a warming climate. And as I mentioned, in our previous work demonstrated that even those very same climate models that do not project a large mean change in winter precipitation in California, or are perhaps uncertain in what the sign of that change might even look like, are quite clear that the wettest wets will become wetter, and also that the driest dries will become drier, leading to an increase again in this case precipitation whiplash that is especially pronounced across Southern California and parts of the desert Southwest. And we've certainly seen anecdotes that align with that in recent years. So drought itself is primarily in the Southwest being worsened so far by increasing evaporative demand rather than large decreases in precipitation. This is a similar plot. This is a plot for all of the southwestern US states, but it's actually rather similar if we only restrict it to California. And essentially what's going on is the same amount of rain and snow just doesn't go as far as it used to from an overall water balance perspective. There has been both more precipitation on fewer days, but less snowpack overall. That contributes to mountain and higher elevation increases in drought. But stronger evaporative demand is contributing towards worsening droughts just about everywhere in the Southwest. And one way to think about this is that droughts in the 20th century used to be hot or cold. You could get a negative precipitation anomaly with either warmer or cooler than average conditions. But these days, we've seen enough warming that we're just not seeing droughts anymore that co-occur with temperatures that are anomalously cool from a historical context. And so this means that virtually all droughts that are occurring in this part of the world now are effectively hot droughts. So blame the expanding atmospheric sponge for that one. Relatedly, there is now pretty abundant evidence that the most extreme fire weather conditions are generally increasing in most fire-prone regions on Earth. This is some interesting work that came out just a couple of years ago looking at the global trend since the late 1970s in extreme fire weather conditions, 95th percentile fire weather days globally. What's striking is not so much that every place on Earth sees a large increase, but that few, if any, places see a meaningful decrease, while quite a few places see large increases. And that, of course, includes a lot of the places that we've heard about in the news, the Western United States, the Southern Mediterranean, Southeastern Australia, and the Amazon, and other portions of South America. But what I find more interesting here is that there are so few decreases. There's a few regions in the Indian subcontinent, the highlands, the foothills, the Himalayan foothills. But really, what we see is the universality of the fact that if atmospheric evaporative demand, the vapor pressure deficit, is increasing over virtually all global land areas quite quickly. That in combination, partly caused by the rising temperatures themselves, are driving this really homogeneous increase. Maybe not homogeneous, but I guess we should say ubiquitous in sign. Where there is a change, it's pretty much always positive because of the aridity increases we're seeing driven by increasing evaporative demand. And this has been studied most extensively in the Western US, where there is evidence, at least in forested ecosystems and forested settings, that there's an exponential relationship between vegetation dryness and area burned, acknowledging again that area burned is not the be all and end all of fire metrics. It is a useful one, at least in the sense that we have relatively good records of it and can make these sorts of assessments. We've seen a lot of regions on Earth, as I mentioned, that have already experienced pretty profound shifts in the upper tails of the vegetation or the fuel aridity distribution driven by increasing evaporative demand. And one consequence of all of this is that it was once believed in many places that the future of wildfire would be somewhat inhibited, or that there'd be a negative feedback, because initially there'd be such a large pulse in area burned that subsequently there would be less and less fuel available to burn. And that is still a dynamic that will likely play out in some places. It probably already is. But if we think more about the non-mean state metrics, the fact that many of these ecosystems may transition from one vegetation or ecosystem type from another, so from a forest to grassland or scrub, or even woodland, where there's more of a rapidly responding herbaceous fuel component, those are going to grow back pretty quickly in an environment of increasing hydroclimate whiplash, because you do still need those wet periods for that abundant fuel and vegetation regrowth. To the extent that we cycle more and more frequently between those conditions, that actually might be offer less of a constraint on future fire area burned, because even though we may be transitioning from perhaps forest fires to other types of fires in some of these ecosystems, we may actually be transitioning towards ecosystems that are subject to more frequent fire in many cases, and in ecosystems that can rapidly accumulate quite high fuel loads in this increasing variability, moisture variability environment. So again, I'm not sure how much formal research there is on that specific angle yet, but there is evidence that there may be less of a negative wildfire fuel reduction feedback than once had been believed in some ecosystems. And in California, we've already seen that autumn fire weather extremes have approximately doubled since the early 1980s. So not a larger increase than in winter, but still both quite substantial. But I think the important thing to recognize is that we're going to continue to see warming in California and elsewhere, because we are not on a path to rapidly halt that climate change that we're currently seeing. There is, of course, a question of where we end up in a wide range of possibilities. If we get lucky, perhaps we stay closer to 2 degrees centigrade of global mean warming. If we get unlucky, we could still end up at 3 degrees or above, which would be a whole lot of additional warming, hopefully closer to the lower end of that range. But either way, that's still a substantial amount of additional global warming and an additional warming and increase in evaporative demand in California. So the climate change related component of wildfire risk in California is going to get worse before it gets better, which means actually that one of the most important things we can do in the near term are things that are not necessarily always related to the climate change component of the risk. It may ironically be the case that we have such strong evidence for continued increases in wildfire risk due to climate change that we need to aggressively pursue non-climate change related interventions to rapidly offset that risk, given that we can't immediately halt that warming and that climate caused increase in risk. There are other aspects of that risk that we actually have a lot more local and state level control over, at least if we choose to address them meaningfully. So I'll get back to that in a moment. Hopefully we'll have some time. If not, let's chat about it in the discussion section afterward. Some of these other non-meat state changes that I think are going to be important are the projected narrowing of California's precipitation accumulation season. Again, these are the very same models that produce small or sign uncertain changes in annual mean precipitation, but nonetheless still project a substantial sharpening of California's already seasonally accentuated precipitation cycle. Now, that's a bit of a tongue twister. I'm glad I got through it. But this means a potentially drier autumn and drier spring and a slightly wetter winter. So even a typical season might itself experience more season to season whiplash, if you will, in addition to the increase in this interannual variability. This has pretty major implications for wildfire risk, especially in autumn. Why am I more concerned about the autumn shift than the spring shift? Well, that's because in these projections, the autumn shift is occurring at the end of the fuel desiccation season, whereas the spring shift means you get some additional fire season, but following the wet winter, when conditions, at least at a landscape level, are generally going to be pretty wet. So I'm not so sure that there's a symmetric risk response here. It's quite clear that lengthening of fire season on the autumn end is going to be more problematic than lengthening on the spring end, at least when it comes to the risk of dangerous or fast-moving wind-driven wildfires that threaten the urban interface. And I think this figure helps illustrate why that is. This is just a schematic, by the way. This isn't necessarily actual data, but it does illustrate what I'm trying to point out here, which is that there is a peak in vegetation flammability, depending on where you are in California, somewhere from late summer into mid-autumn, depending on where you are. And in California, again, depending on where you are latitudinally, that partially overlaps with what's known as, I guess, strong offshore wind season. In Southern California, this would be Santa Ana wind season. In Northern California, this might be the Diablo or Jarbo Gap season. But there isn't perfect alignment between peak vegetation flammability seasonally and peak offshore winds, generally speaking. But if we extend fire season by a month or two, and again, depending on where we are, that might be from September to November, or from October to December, or in Southern California, even from October or November all the way into January, as we saw this year, that can greatly increase fire risk in a non-linear sense, because we're preferentially increasing the risk on the very highest risk days because of the prevalence of those strong, dry offshore winds peaking at roughly the same time of year each year, and without a large indication of a strong climate change component there. So just by shifting or extending the peak of that fuel aridity or that landscape level flammability just a month or so later in the season, that's not just adding incrementally more fire season days, but it's particularly adding them at the highest risk portion of the year, especially if we're concerned about wind-driven fires. And as we can see, this is just some footage I took in Colorado a few years back from an unusual autumn fire. This is a large fire vortex that occurred on a strong downslope wind day at a time of year when there's more often than not snow on the ground. The snow arrives early when you're over a mile up. It just goes to show you that these kinds of conditions certainly weren't unprecedented historically, but just by shifting that season by a few weeks or a month, as was the case when this occurred, you can get pretty dramatic effects on the ground. And these are some thoughts that are sort of a mix of research and some personal observations from recently. I'm going to try and wrap up the talk in the next 5 minutes so we have at least some time for discussion. But there are some additional reasons why autumn and winter in particular bring maybe additional considerations beyond what we're used to when we think about the warm season or the summer in the Northern Hemisphere being the sort of the canonical peak of fire season. That's partly because in downslope wind corridors, this would include the Santa Ana wind corridors in Southern California, the Diablo or Jarbo winds in Northern California, as well as these somewhat less common but still consequential winds in the Cascades, on the lee side of the Sierra, which can be, well, either side of the Sierra, depending on the prevailing storm track, and the leeward slopes of the Rocky Mountains, as is illustrated in these images here, all of which I took, again, during the cool season between October and March, just within a 5 mile radius of our home. There is a strong potential for relatively incremental shifts in vegetation aridity seasonally to cause large changes in fire risk, especially in places where this overlaps increasingly in these downslope wind corridors with peak downslope wind season. Because you often have a circuit breaker effect, where if you have a significant precipitation event that precedes a strong wind event in these places seasonally, you just don't get this kind of fire behavior or this fire risk because it's just too damp. You might still get fires, or you might not, but they aren't going to have the same sort of behavior that they do if you still haven't seen any precipitation seasonally and vegetation is still at critically dry levels for longer than usual. So in that sense, there's this nonlinearity due to the seasonality and the nonlinear overlap between the joint union of these conditions. We also have another consideration in terms of the vegetation phenology. In a lot of places, the vegetation can go at least partially dormant in winter, leading to lower live fuel moistures. That's not always true in California. The winter often is the grass green up season, although not always if we have a severe drought, as was the case up through January this year in Southern California. And this can occur either generally in some places where the winter is the dry season, or also episodically, even in places where the winter is typically wet if you have an exceptional drought. So this is a case where, again, the non-mean state might be really important and behave quite differently due to the asymmetry of the underlying phenology of the vegetation itself. This is true too in places where you have a lot of deciduous trees, and also in the wild and urban interface where there's a lot of deciduous street trees. If you do get a wildfire in autumn, those autumn leaves are going to blow around during a wind event and can become a pretty extensive contributor to the firebrand load during those woolly fires in autumn that you tend not to get at other times of year. There's also even a human behavior component to this that I haven't seen discussed as much, which is that often in the people's yards or in city parks or medians, places that normally have irrigated vegetation, so even people's lawns, for example, often the water goes off in winter because either in California it's expected to be the rainy season and so people stop watering and irrigation systems are turned off, or in colder regions like the Rocky Mountain Front Range, for example, you have deep freezes in winter and so you have to turn off the irrigation systems so they don't break when it freezes. That means if you do have a fire during strong wind conditions, you now have an urban landscape that is primed to burn because you have dormant vegetation. You have vegetation that has been deliberately not irrigated in places where it otherwise would normally be. And you also have a bunch of essentially standing dead fuel in the form of wooden fences and wooden decks that act, according to my understanding, pretty close to kiln-dried 100-hour fuels, where you have them in a wildland urban interface type fire, or an urban fire, as we see when these fires move ever farther into the urban fabric, as they did in many recent cases. And so really just pointing out that there is actually some reason to think a bit differently about fires occurring in the cool season in winter, both due to the nonlinear effect from the overlap between dry vegetation season and also due to things like vegetation phenology, the seasonal dormancy of vegetation, and even human behavior in populated areas where we stop irrigating a lot of our yards, our parkland, and our ornamental vegetation in a way that becomes a pretty big hazard if a large urban interface fire does come along. I'm going to zoom through this, unfortunately, because I know I'm running short on time, but just to point out, um, prescribed fire and other fuel treatments have been discussed extensively as a major and promising risk reduction intervention, ecosystem restoration intervention, especially in places where there has been an accumulated fire deficit due to suppression activities over the past century or so. Prescribed fire usually occurs under a just so set of conditions where obviously it can't be too damp or you don't achieve your objectives. It can't be too dry and windy or it gets a bit too dangerous. We did find in a study published a couple of years ago that climate change is broadly going to decrease the number of days favorable for prescribed fire treatments across most of the Southwest US, including most of California. But interestingly, the seasonality is not uniform, and there are a lot of places, including much of Central and Northern California, where there actually might be more prescribed fire days in a warmer climate in winter specifically, pointing to, again, not only nonlinear and seasonally dependent changes in fire risk, but also arguably seasonally dependent changes in fire, I guess we could call them opportunities, in terms of risk reduction and ecosystem restoration that might have to take place in winter if we have the ability to take advantage of it. So just to sum it all up, by focusing on mean trends, I really do think we're missing important information and potentially underestimating the contributions by climate change to wildfire risk, particularly when it comes to the extremes and the seasonalities involved with both the meteorology and the ecology of these systems. And in particular, I'm interested in the frequency and magnitude of fuel accumulation desiccation cycles and the increasing overlap between critically dry vegetation and strong wind seasons. And there's additional questions even related to human behavior, things like irrigation in the WUI, for example, that are themselves seasonally dependent that we probably need to be thinking more about. So as we all know, I think at this point, wildfire trends are multifactorial. We can't just say it was caused by X or Y or Z. It's X and Y and Z to varying degrees in varying contexts. Um, eh, and while the effect of climate change is decidedly quite variable across individual events, ecosystems, and other contexts, it really is there pretty much all of the time now. It can be small in some cases, or maybe even the dominant effect in others, but it's not something we can ignore. And I think we ignore the extremes and the seasonality contributions at our peril, because those may in fact be some of the most important contributors overall. These seasonal shifts, in particular, can potentially have net effects in terms of risk and, as I mentioned, also prescribed fire opportunities that are larger than the sum of their parts. And specifically, some of the things that I think we need to take a closer look at are this notion of increasing hydroclimate whiplash, which can accelerate or amplify fuel accumulation and then desiccation cycles, particularly important in grassland and shrubland ecosystems, but also there's evidence that this matters even in dryland or semi-arid forests to a significant degree as well. And also this notion, this can be important everywhere, including even in moisture forest regions, the increasing overlap between dry vegetation season and strong, especially downslope wind season, as well as the interactions between the ecology, the phenology of the vegetation itself, and long-term trends. And I just like to end on this slide when I talk about wildfire, because I think it's a really important thing to remember for any number of audiences. Even though I know that a lot of folks listening today think about this a lot and articulate it, it's not wildfire itself that's necessarily the problem. That wildfire is not inherently bad. It is a natural process. In many places, we don't have enough fire on the ground, but it really is this intersection between populated areas that has become quite destructive, arguably catastrophic, and it is quite foreseeable we could see even worse fire disasters in the future. I've had a version of this slide now for almost 10 years, and every couple of years I add a new, even more destructive event to the images here. So I think the burning question ultimately is this. Not so much can we decouple fire from catastrophe, but the updated version is will we? Because I think we know what it takes to do so, as has been talked about by others in the seminar series as recently as the past couple of cycles. But the real question is whether we're going to successfully implement those changes quickly enough to offset all the other factors that are increasing risk. It's my sincere hope the answer is yes, but that is going to take a lot of active effort. So with that, I'll close. I know I'm running a bit long, but hopefully there's still a bit of time for some questions from the audience. So thank you.
Well, thank you so much, Daniel. That was an incredible presentation. And yes, due to time constraints and high attendance, we kindly ask you to put all questions submitted through the Q&A chat. And for our first question, Daniel, is from Joy Yang. And I'd like to condense a couple of these, but do you see differences between El Nino and La Nina years in terms of winter fires and summer fires?
It's a good question. I haven't looked at it so specifically. I mean, there's really, if you were to do an analysis of this, there's a couple of considerations. One is that El Nino and La Nina are not the be all and end all, as most climatologists will point out. They really matter most when they're in their extreme states. So a particularly strong El Nino might exert a considerable influence relative to a particularly strong La Nina. But it's not so clear that this binary separation of El Nino and La Nina itself is enough to be meaningful. We might expect that the strongest El Nino events will probably bring wetter conditions in Southern California. So I suspect that would likely decrease the late season or the winter fire risk there, and perhaps somewhat the opposite to be true for strong La Nina events. There's less of a signal farther north you go in California. There's also the question of how this might affect the occurrence or the intensity of Santa Ana wind events. There's some indication that strong La Nina events are a bit more conducive to strong offshore wind events. So there might be a sort of a bit of a double whammy there with a slight increase in the odds of low precipitation and maybe of offshore wind conditions to a certain extent. But I'm not sure that it's enough at seasonal scale to tell us much about the big shifts in risk. I would argue that in many cases, the existence of a pre-existing drought or a long-term trend towards increasingly dry landscape conditions might end up being a more helpful predictive factor at longer timescales.
Great, thank you so much. And then a question from Benya is, hydrologically, you mentioned variation in precipitation. How about other places along the hydrological cycle? Lake, snow, ice catchment, river, flow, flooding, ocean effects, and especially groundwater. What are the differences? What are the different human dependencies and vulnerabilities at each point in the cycle over seasonal and longer time and across geographic location?
Well, that's a very good PhD dissertation that I don't think I have this time to respond to comprehensively in the time we have left. But I do think it's an important. The framing I think is actually really important here, where I think my point that I would make succinctly is that in all of these things we do need to be thinking about the non-mean state conditions and the seasonality. It's not enough to look at annual mean trends for any of these things. In fact, there's even evidence, I think, with observed and projected stream flow, for example, in many parts of California, that the average annual stream flow is not necessarily decreasing, but that it's the amplitude of the seasonal cycle is becoming a lot more amplified, which is that the driest or the lowest stream flows are becoming even lower, and the highest stream flows are staying constant or even sometimes increasing. At least that's to a certain extent, the observation and a stronger projection about the future. Snowpack somewhat behaves similarly. We've seen a long-term decrease, of course, in the overall snowpack. But we've not seen a decrease in the most extreme snow accumulation years. So interestingly, what we seem to be losing are the robust snow accumulations at moderate elevations in the mountains. And what we're losing are those average snow years. We're still seeing the really big snow years, but we're also seeing a lot more years with very low snowpack. So there actually is an increase in the snowpack variability, interestingly as well. That's a bit more complicated than just precipitation because that also involves temperature, of course. But there's a lot of interesting things going on here that are you start to pop out of the woodwork when you look beyond the mean trend.
Great, thank you. And then Ellen had a question about, with respect to the 95th percentile of the fire weather index showing only that it's increasing, could snow albedo effect in winter and spring be affecting this?
It certainly could be in places where there's a significant historical snowpack. We know this is true in the higher elevations of the Rocky Mountains and the Sierra Nevada and the Cascades, where In snow-dominated catchments, the fact that you lose that highly reflective surface early in the year, and perhaps more importantly, that you lose that gradual replenishment of soil water throughout the summer earlier than you would if that snowpack stuck around longer or was more extensive. We do know that the snow drought years, for example, so places that have anomalously low snowpack, even if the overall amount of precipitation is not necessarily below average, in those largely forested settings, do tend to see increased fire activity in those years relative to other years with similar amounts of precipitation overall. So, there is something that is protective about that snowpack that, if it lingers into May or June or even July at the high elevations, some years, obviously, that's going to greatly inhibit your ability for higher intensity fires. The more you lose that in those settings, the more you can see that. I don't think, though, at global scales, that's a dominant effect because most of these places are not places that get a whole lot of snow. There are some, but I think the dominant effect here really is this increase in atmospheric evaporative demand, this rise in the vapor pressure deficit and of overall fuel aridity, although these shifts in snowpack in many places outside of perhaps the high Arctic would also be contributing to the fuel aridity shifts too.
Great. And if you wouldn't mind, I wanted to end on, I have a question for you. I worked in the post-fire reforestation world, and I just wanted to hear your take on the management implications of these whiplash events on reforestation in California, especially when the first years of reforestation is really critical in terms of soil moisture and available precipitation for these young seedlings being planted.
Yeah, I mean, I think it's a bit of a mixed bag. There is a bit of good news in it, which is that I think the future looks a bit different than one in which it just perennially became drier and drier and drier in California with less and less precipitation. I think in that reality, which does not necessarily appear to be the most likely future, it would probably be pretty hard to reforest a lot of these regions if you just got less and less water. I think we will see drier and drier dry periods. What it might end up meaning is that replanting might need to be strategic. There might be some years and some periods where it probably a lot of those seedlings are not going to be successful because you're in the middle of a really severe drought. But then if you wait a year or two, it might well be that those are some really favorable growing conditions during the next wet cycle. So I mean, there may even be a bit of an opportunity there relative to a world where everything just got perennially drier. But it also poses challenges in the post-fire regime because, of course, what is going to be able to take advantage of that whiplash cycle most readily are things like invasive grasses. So you might see these fire footprints fill in quite quickly with invasive grasses that are themselves fairly flammable too and can outcompete native plants. And so that's sort of, an intermediate challenge. How do you manage these post-fire landscapes for, post-fire flood and debris flow risk is one concern with this increase in variability. But another one is, of course, the success of replantation and the prevalence of invasives that really can take advantage of variability to begin with. And so I think there's a lot. This does have, I think, a number of direct implications there, and depending on how well you're able to sort of roll with the punches, as it were, it will sort of depend on how good or bad news it is on balance.
Thank you, Daniel. And as we wrap up today's session, I just want to thank everyone for joining us. Again, special thanks to Daniel Swan for his enlightening presentation. And our next session is scheduled for March 11th at 10 a.m. on Tuesday. We'll be discussing lessons learned from LA wildfires from UC Cooperative Extension Forest Advisor Yana Yalakovic. And then before we sign off, please keep an eye out for those webinar evaluation forms that'll be sent out soon. Thank you once again, and I look forward to seeing you guys all in future sessions. Hope you have a great day.